Okay, this is our lecture 16. Today we're going to finish our discussion about this topic, measures of associations. And so last time we talked about the first and most widely used correlation called Pearson correlation. It is used to capture linear relationship between two scalar value random variables, x and y. So what we emphasize here, in addition to what you have learned before, is that there is a population Pearson correlation you want to do statistical inference for, and there is a sample Pearson correlation you can calculate based on your data. So I didn't talk about the specific test for about a hypothesis regarding whether like the population correlation being zero, that's the null hypothesis, and the alternative being not zero, then you can use your sample Pearson correlation to construct a test statistic and then do the test. So Fisher has the Fisher's Z test for this purpose, and you can check that out yourself. So due to the time limit, we're going to ignore that part. And second, we talk about the monotone relationship. For this part, we introduced the Spearman rank correlation and Kendall's tau. So these two are widely used. And Spearman rank correlation has a very straightforward interpretation as that you just convert your data from their actual, for each variable, you convert its actual numbers as its observations into ranks. And then you have two vector of ranks, you compute their Pearson correlation. That's what you call Spearman rank correlation. For Kendall's tau, you need to define pairs of your observations as concordant, discordant, or neither. And then you will combine the number of concordant pairs minus the number of discordant pairs over the total number of pairs. That's how you define Kendall's tau. Compared to Spearman correlation, Kendall's tau works better for when your data has too many ties, because those ties will be called neither. Okay, the functional relationship is a bigger class of relationships where you see there is a functional relationship in the mathematical sense, and then you have noise in addition to that relationship. So if this relationship is not monotone, then you will not get a perfect correlation as equal to 1 or -1 with Spearman correlation, even though the data points lie perfectly on a function. So to address this issue, maximal correlation was proposed as a mathematical concept as the absolute value of Pearson correlation, considering transformations of x and y, and you want to take the maximum over all allowed transformations. Okay, this is a very nice concept. So in theory, it can capture any functional relationship. And also a nice property about this definition is that whenever you have maximal correlation equals 0, you can claim that your two variables are independent. Here, the independence is in the probability sense, which means that changing values in one random variable has nothing to do or conditioning on one random variable, the distribution of the other random variable is not changed, no matter how you change the variable being conditioning on. So that's the rigorous definition of independence. And maximal correlation has that equivalence with independence. That's very nice. Okay, but on the sample level, how do we calculate the maximal correlation given a set of data points? That's the question that hasn't been addressed in the pre-computer age. But in the 1985, an iterative algorithm called alternating conditional expectation was proposed to address this issue. Okay, so here, this is the formulation. So given that we have the flexibility to choose F and G, right? So what we can do is that we can consider F and G such that we can restrict our transformed Fx to have mean 0. So is our transformed Y, so-called Gy. So we restrict both to have mean 0. That's how we can shift our function by, so for example, if a function we pick Fx doesn't have mean 0, we can always add a shift to F so that we can make expectation of fx equal to 0. And here the expectation is for the random variable x. This is for the random variable y. And moreover, we can do scaling. So we can constrain that the variance of fx and the variance of gy is equal to 1. So this can simplify a lot of things for us. The reason is that if two random variables both have mean 0 and variance as 1, then their correlation, their population level Pearson correlation, which we call fx gy. Oh, by the way, based on our previous notation, this Pearson correlation, we use the notation rho. So I'm going to stick with that. So this can just be equal to the expectation of their product. This can be seen from our population Pearson correlation right here. You see, whenever x has variance 1, y has variance 1, then their covariance is just equal to their correlation, right? Because the variance is equal to 1, variance is equal to 1. This is just equal to the correlation. And this covariance, if you recall, its formula is expectation with x minus expectation of x multiplied by y minus expectation of y. And since expectation of x is 0, expectation of y is 0. So it becomes just expectation of x times y. That's why these two constraints will make it convenient for us. Okay, and then we know that these two things will give me the expectation of fx squared equals to, I should put a square inside, the expectation of gy squared will be equal to 1, because this expectation is equal to the mean squared plus variance. That's 1. So because of those, I can see that then if I do the expectation of fx minus gy squared and I open it up, then what I would have is the expectation of fx squared plus the expectation of gy squared minus 2 times expectation of fx times gy. Okay, and I know this is 1, this is 1. So I get 2 minus 2 times expectation of fx gy. And then you can see, because of this relationship, then if I want to maximize this term, the expectation of fx gy, which is my maximal correlation, if I want to maximize this, it's equivalent to minimizing the left-hand side. So what I mean is that the argmin in terms of fg of the left-hand side, expectation of fx minus gy squared is equal to the argmax of expectation of fx times gy. And this is exactly the thing we want to maximize, right? The argmax rho fx and gy. So therefore, this allows us to transform the question of finding f and g to maximize the Pearson correlation, maximum Pearson correlation. So one thing I didn't say yet is the sign, sorry. So in the definition of maximal correlation, we have the absolute value, right, to make it non-negative. But this can also be done by making the f and g such that this correlation is positive, because if not, I can always multiply f by -1 to make their correlation positive. So that's not an issue. So that's why I can drop the absolute value here. Okay, so therefore, you see, essentially we changed the problem to this minimization problem. And this is what we call squared loss, right? We take the difference and we square the difference. We want to find the minimizer of that. And this is why we have alternating conditional expectation. So the idea is this. Okay, so let's see that given f, let's say f is already fixed, then what is g? Then what is the g that minimizes this fx minus gy squared? That's the first question we want to address. Given one function, how do we find the other function? To answer this question, what we need to say is that, okay, when f is given, you can just think of fx as one random variable. Then the question is, how do we find a transformation on y so that gy is close to fx as much as possible? And here the closeness is in terms of expectation. So this is essentially very similar to a regression problem. You can think of g as the regression function we want to find. Here the y is regarded as your predictor and fx is regarded as your response. So how do you find that? And in this case, actually we can show that the regression function that minimizes the square loss is basically the conditional expectation. Okay, so it's actually the conditional expectation because g is a function of y. So it's actually the conditional expectation of fx given y. So the answer, you can show that yourself. How do you do it? Basically, you just need to, because this g is the target you want to find. So what you want to do is that you can basically try to take the difference, let me see. Yeah, you can try to open up the square and show that, okay, probably you can do this. You can do the minus the expectation of fx given y and add back that expectation of fx given y. And then you can open up this square loss and see that that's actually the thing you need. Okay, I'm going to skip the technical detail for that, but just to give you the answer. So we can show that here the g is going to be of y is going to be the expectation of fx given y. Okay, that's the answer. And this is the answer you can see from the definition of conditional expectation. It's making sense. That is, you want to make your y very, very close to fx. So fx is your target. And g is a function of y. So this part must be a function of y. So whenever y changes, the right-hand side must change. But it has nothing to do with the particular value of x, right? Because x is a random variable, it can take different values. So what you do is that you take expectation for x. So with expectation, x is gone. The function has nothing to do with the random variable x, and it's only conditioning given the y. So whenever you change y, you change the conditioning, and so you change the expectation. But we see that intuitively, you can see this definition of gy is going to make gy very close to fx, since our target is fx. It's just that we're taking expectation over all possible value of x. Okay, that's the answer. So similarly, you see, given g, if you want to find the f to minimize the square loss, the answer is going to be expectation of gy given x. Okay, so it's alternating. That is, given one function, you find the other function by taking this minimum or this minimizer, and given the other function, you update the first function by taking the minimizer formula. So you alternate between those two steps. And what you need to guarantee is that in every step, you need to make sure on your data the mean is 0 after transformation. And the variance, the data variance is 1 after transformation. So as long as you keep doing that, and in this step, okay, so in the update step, what would you do? So how would you take the expectation of fx given y? So this is my plot. So probably the plot is more intuitive than the mathematical formula for some of you. So on the sample level, you can see that, let's say that given we are in iteration k, okay? So let's say we are in iteration k, we find fk. Then what we do is that find gk as this. You can do this piecewise regression. So what we mean is that here, your target is to make your y very close to x. So let's say that your yi's are here, okay? So these are the yi's, and these are the fkxi's. So you apply the transformation to your x1 to xn, you plot them in the y-axis, and you plot your original yi in the x-axis. So let's say that if your data points now look like this. So then what you do is that for every neighborhood of yi, you are going to do this, okay? This means that you are conditioning on a particular yi. And then you take the expectation of fkx. That will be the average of the points in the neighborhood. And that will be what you call as the G. So let's say this is yi. Let's say this is y3, okay? Then this will be what you call as gy3. So you do that for every point. So essentially, it's like a smoothing. It's a smoothing problem. You want to find a regression, nonlinear regression line through the scatter. And then for every yi, you find its local average, right? The local average for its prediction. That's what you're going to predict as GK y3. So you do that for GK y1, y2, y3, y4, y5, and so on to yn. So you will get the GKs. So that's the transform values. And then next step, you are going to plot. Next, you are going to find fk plus 1 in the next iteration. So over there, you are going to plot now xi's in the x-axis, okay? And now you are going to plot gk yi in the y-axis. So let's say that if the data points looks like this, then you are going to find another regression line through it, and you are going to call the fitted values on the line as your fk plus 1 xi. So that's how you're going to update every step. But just make sure that after each update of the function, you need to make sure it's centered at 0 with variance 1. So you need to do that for every step. So for example, what I mean is that, so once you get those G1, GK, so with, let's say GK, Y1 to those GK, yn, right, the endpoints, you need to make sure that they have mean 0 and standard deviation 1. If not, you're going to standardize them by doing that. And that will be your GK y1 to yn that's going to be used here in the next step. So that you're going to find fk plus 1 for x1 to xn. And then with those, you're going to do centering and standardization again. And then you alternate until there's nothing to update. Okay, so basically what you do is that with those, you are going to compute what we have here, the loss function. So you are going to compute this thing, the summation I from 1 to n, the square of fk xi minus gk yi square. Okay, you stop until this value no longer changes. Alternate until convergence. This is what we call alternating conditional expectation. So it will allow you to find some relationship between some transformation on X and some transformation on Y so that you will maximize their correlation. That's the idea. But as you can see, the technical challenge is on this local nonlinear regression. There are multiple ways of doing that. You could do local smoothing like piecewise, in a piecewise way, or you could do polynomial regression, or you could do a smoothing spline. So that's what we call in statistics called non-parametric statistics. So you go beyond a linear model, and the model may become very complicated with many parameters, but you just want to make sure that you're not overfitting the data. So there are issues that need to be considered in that case. And we skip that detail about the technical thing, but we just give you the idea of how this algorithm is going to be implemented. Okay, that's maximal correlation. If you want to give it a try, there's an R package, and you're going to try it in your next homework. So it's called the ACE pack. So it stands for Alternating Conditional Expectation, ACE. So you're going to try that for computing the maximal correlation on your sample. That's the first measure we will introduce for computing, for capturing functional relationship that is not necessarily monotone. All right, do we have questions about maximal correlation, at least the sample level implementation? Okay, so if not, let's move on to the second measure I will introduce for functional relationship. This is a more recent one, but I think it's I think to me, it's a very fundamental and useful one. So this is called a distance correlation. And I happened to meet the author of this paper, and I was very impressed by the fact that they actually spent more than 10 years of efforts in developing this measure. And once you read about it, you'll be shocked by how fundamental it seems to be. So it's very impressive to me that nowadays we can still see a measure or a research paper that tries to tackle such a fundamental problem. So that's very encouraging. So this is by Dr. Zackley and his student. And his student in 2005 and 2007. So they have, so I just put it here. And his student, they have two papers. One focuses more on the math, the other more on the application. So the distance correlation is very unique, and it's different from everything we have talked so far in that here the X can be of any dimensions and Y can be of any dimensions. We no longer require them to be scalar value or one-dimensional. So for example, your x1 to xn may be n images, and your y1 to yn may be n labels. Let's just put it that way. So we don't require that x and y are in the same space. Okay, so the two random variables, x and y, can be in different spaces. So like I said, each x could be a random matrix, and each y could be a random scalar or a random vector. Their dimensions don't need to be matched. But still, your sample will always have pairs. So your sample is still written as x1y1 to xn ym. So the pair information is always needed if you want to talk about relationship between two random things. Okay, so how do we address the issue that the x and y may be in different space, right? How can we link those two? For example, if you look at here in the maximal correlation, if x and y are in different space, then f and g are also functioning in different space. And this approach we take here will not be really implementable or easy to implement. Let's say if yi is multidimensional, xi is multidimensional, how would you imagine this picture would be like? That would be very difficult to imagine, right? So let's say if yi is two-dimensional, xi is two-dimensional, then if you want to capture the relationship, you need to imagine not a three-dimensional space. That's not enough. You can only imagine a three-dimensional space. Let's say if yi has one-dimensional, xi has two-dimensional, probably you can think of it as or let's put it another way. Y is two-dimensional, x is one-dimensional. You can think of it as a surface in a three-dimensional space. But if you go more than that, that's very difficult to imagine how you are going to do this. So that's why this you already get some sense about what we call the curse of dimensionality. When you move from one dimension to multidimensional, things always get much more complicated. And that's the case here. So distance correlation try to get around this issue by saying that, okay, I don't need to connect X and Y based on their measurements. I just need to be able to compare different X's and different Y's within their own space. That's the idea of distance correlation. So we're going to convert our data into pairwise distances in the space of X and pairwise distances in the space of Y. And we're going to use those distances, which are scalar values, right? Non-negative scalar values. We're going to use those to come up with a measure. That's the distance correlation. So I'm going to skip the population as again, due to the time limit and due to the technicality. So we are going to talk about the sample distance correlation, how you are going to compute it on your data. Okay, so let's just say that, for example, let me make this up. Let's say my x1 to xn are p-dimensional. For example, you can consider them to be n patient samples. For each sample, you measure p genes, okay? And then let's say that y1 to ym are q-dimensional. You can still think of they represent the same n patients, but each yi is the ith patient's like clinical measurements of q dimensions. So like these data are clinical measurements, these are gene expression data. They are clearly not in the same space and not directly comparable, but they are paired based on patients. So given this data, our first step for calculating the distance correlation is to define pairwise distances within each set. So we can define Aij as the pairwise distance between xi and xj, between two patients in the X space. So for example, it could be the Euclidean distance if you want, or you may want to use other distance metric if you think Euclidean doesn't satisfy your desire. And similarly, we need to define Bij as the distance between yi and yj in the Y space. For example, you may still use the Euclidean distance or some other distance. So, okay, so then you will have n by n Aij's and n by n Bij's, right? So two matrices. So then what we're going to do is that we are going to do double centering on those matrices. What I mean is that, so if you think of a matrix, okay, so I'll put A11 to A1n, AN1 to ANN. That's the matrix of the Aij's. I can also put B11 to B1m, Bn1 to Bnn. That's the second matrix. So I'm going to do double centering, which means that for each entry, I will subtract its mean, this row average, I will subtract its column average, and I will add back the overall average of the matrix. The reason I need to add back is that I actually did two subtractions. So that's why if I don't add the if I don't add the overall average back, then the center distances will not have mean zero. So that's what I need to do that. So to put it in formula, what I mean is that I define or I denote AI dot bar as the average of row I. So it's just like 1 over n summation aij, j from 1 to n. I take the n values in row I take the average, and a dot j bar is the column j's average, and it's just 1 over m. Here is I go from 1 to n, aij. And I have the overall mean. The overall mean is a dot dot bar, I call it. It's just 1 over n squared, summation I, summation j, aij. Okay, so that's the overall average. And similarly, I will define bi dot bar, b dot j bar, and b dot dot bar. So with this, I define double, or I should say doubly centered distance based on AIJs and BIJs and their row means, column means, and overall means. So I would have a capital AIJ defined as AIJ minus AI dot bar minus A dot J bar plus A dot dot bar. I added back the overall mean. And I define BIJ as bij minus bi dot bar minus b dot j bar plus b dot dot bar. Okay, so the reason we do this double centering is because of the nice property that is for these AIJs, we are going to have the summation of AIJ, I from 1 to n, would be equal to 0. And if we take the summation for j from 1 to n aij, it's also 0. And the overall sum ij aij is still 0. So I will have this nice property for the doubly centered distances. And the same conclusion held for bij's. So if I change this to ibij equals to summation j bij equals to the double sum ij bij. This is also 0. Okay, so with those, then we define what we call the sample distance covariance. Sample distance covariance. So we will write it in short as DCOV. Okay, distance covariance between X and Y. So I'm going to write the problem because I want to emphasize that this is the sample distance covariance. So I would put a hat here, okay, to mean that it's estimated from our sample about the two random quantity X and Y. Let me try to do this. Then it's defined in a very simple way. It's just the average of aij times bij. So we do the product of the centered distances and we take the average for all pairs. That's the sample distance covariance. And now with covariance, the variance is straightforward because variance is a special type of covariance where the two random quantities are 1. So therefore, we have sample distance variance for X and Y. We write them as d var hat X. So for that, you can tell me what it is. Just changing this bij to aij, right? So this is just dcov xx. And that's just 1 over n squared ij aij squared. That's it. And similarly, we will have distance variance, sample distance variance of y. And this is clearly y and y. And this is just 1 over n squared. ij bij squared. Okay, so with this, we have the sample distance covariance, sample distance variances. Then we have sample distance correlation, just based on how we define the Pearson correlation. Then sample distance correlation is defined as d core. Okay, I still put hat here to mean this is a sample version. It's just defined as d cov hat xy divided by the square root of d var hat x times d var hat y. That's it. Okay, and we can show that by this definition, it's going to be between -1 and 1. Actually, I think it's 0 to 1, right? Because I don't think this can be negative. Yeah, I think that's a typo in the notes. We need to correct that. So it should be from 0 to 1. So essentially, you see that we don't use the original data directly. Instead, what we do is that we convert our data into pairwise distances between x1 to xn and pairwise distances among y1 to yn. And then we take those two sets of distances to come up with a measure. And how do we interpret that? The fact is that basically, you see, based on this definition, essentially we are measuring whether when two data points are far away in the x space, are they also far away in the y space? If that's the case, then we said x and y should have a large distance correlation. If not, then it's not the case. Does that make sense to you? So we're measuring the relationship between the two sets of distances. Oh, actually, my bad. No, I think it's right. It could be negative. Yeah, my bad. I was confused myself. Yeah, because ANJ and BIJ could be negative by the double centering definition. They are no longer distances. Okay, they are no longer original distances. Okay, so for the implementation of this distance correlation, the original authors have on our package, for the set of statistics they defined based on a similar idea, and they call those energy statistics. So you can check that out. It's the R package called energy. And the command for this calculus is dcore. Yeah, so I think it's dcore. It's this. That I think in the notes there's a double R, which should be removed. So a nice property about the population level distance correlation, although we didn't introduce, is that it has the same property as the maximal correlation. It is 0 if and only if x and y are independent. So being 0 also implies the independence. So I'm just going to put it down here. Population d core is of x and y equal to 0 is equivalent to that x and y are independent. This is also motivation for the development of this whole distance correlation. So you can say, so my suggestion is that when your data x and y are both scalar valued, which means that you can make a scatter plot of your data. When that's the case, you could use either distance correlation or the ACE algorithm for the maximal correlation. But please make sure that when you run the ACE algorithm, don't run it just for once. Because as you can see, as an iterative algorithm, it depends on the initialization. So if you use different initialization, you may get different numbers. Well, based on my experience with distance correlation, there's no issue with that. So it seems to be a good thing. But their nominal values can be different a little, especially when your data are not perfectly on a relationship. Yeah, and also the distance correlation, I want to say one thing. So distance correlation is not guaranteed to give you a value 1 when your data lie perfect on a relationship, like a parabola, okay? But maximal correlation is going to give you a measure of 1 for that relationship. And distance correlation can also be used to capture relationships that are more complex. Anything that's different from independence, it will give you a non-zero value. That's also something to good for. And most importantly, I would say distance correlation is very good for its generalization. That means you don't require X and Y to have the same dimensions, and you don't even need to require to be scalar values. So these are very general. So in some cases, when your data are paired, but clearly, like I said, one is a set of images, one is a set of clinical outcomes, you could consider this distance correlation to see if there are any associations between your X and Y, and then that may lead to some interesting scientific hypothesis. Okay, so I would say distance correlation is just probably, I think I should change a little bit. So not to confuse you. So for functional relationship, yeah, maximum correlation is specific designed for that, but I will call this category 4. I think distance correlation belongs to a big class of measures that can capture non-independence relationships. Yeah, so therefore I should add word here. So these are for non-independence relationships. And this is a very big class of relationships. Anything not independence should be put into here. But clearly you can see the issue is that some relationships are not easy to interpret. So for example, I can tell you that if the relationship is something like this, so let me just randomly make it up. So if I have a relationship like this and data points come from here, it's not something we can easily interpret, but it is not independent. So that's why I'm saying that non-independence is not necessarily a good thing, because you need to make sure your results are interpretable. But still, under this whole idea of capturing non-independence relationships, we have other measures for capturing this. I'm just going to quickly mention them here. One is the famous mutual information. And it's variant. So motivated by this, many variants have been developed. Mutual information is also having the property that it is 0 if and only if the two random variables are independent. But its domain or its range is from 0 to infinity. So there's no upper limit on how large the mutual information could be. So, but realizing this issue in 2011, there was a paper on Science, which is very rare because that paper is only about a measure. It's usually, you will not see a science paper like that. So it was a very big shot in the field about that new measure. It's called a Maximal Information Coefficient. Short as MIC. So that's a 2011 science paper when I was still in graduate school. And I spent quite some time looking into that paper. And at that time, there were a lot of discussion about that new measure. Because in the preface, it was claimed to be like the correlation coefficient of the 21st century, something like that. But the issue with this correlation, because the reason it was not the standard yet, is because that it's basically a normalization of mutual information, to normalize mutual information to the range of 0 to 1, okay? So this one claims to capture all relationships that are equitable. But I think it was questioned by statisticians and mathematicians about the definition of equitable. What kind of relationships are equitable? It cannot be any relationship. For example, like the thing I draw here, it can be regarded as some sort of relationship, but do you really want to capture it? I think that's the biggest criticism the method receives because of that vague definition of equitability. If you're interested, you can check out this paper. And I'm not going to talk about this year because of our time limit. Okay, mutual information, which is from the information theory started by Shannon, is a major type of measure people use to measure the dependence of two random variables. And related to that, there is what we call the Hoeffding's independence test. It's a very famous test for independence, but as we know that it's not a measure, it's a test statistic, and you're going to do a statistical test to get a p-value, etc. So it's not a measure on itself. And after that, there are many methods that have been proposed as measures of association. For example, there's another measure which has received a lot of attention as well. It's called the correlation using principal component. So CorGC. So that one is in our notes. This 2008 paper uses principal component and principal curve to try to capture relationship between two variables and many things like that. And so for my own research, so maybe I can say a little about that. So motivated by the fact that, okay, some relationships may not be functional, which means they are not one-to-one. For example, given one value of one variable, you may have more than one value in the other variable. So a common case for this is to think of this shape. If you have a cross type of scatter plot, which means that your data points may belong to two subpopulations that have different relationships, how do we capture those? So of course, this relationship can be captured by measures of this category, right? This is not independence. So these measures should be applicable. However, these measures are not very powerful for capturing this measure, or capturing this pattern, because they do not specifically look for a combination of linear patterns. They look for all sorts of patterns. So motivated by that, myself developed something I call the generalized R square. So the idea is to generalize the Pearson correlation to this scenario. So you don't need to tell me how many lines there are there. So we can use the data-driven way to detect the number of lines based on something like the k-means. So what I use is what I call the k-lines algorithm. So this is just a way I developed a way to categorize or to divide data points into lines. And then for each line, I'm going to get a Pearson correlation. And the last step is to aggregate the Pearson correlation squares into one measure, which is called a generalized R square. So the whole idea is that even if your data has more than one linear patterns and could be easily missed by simple measures as Pearson correlation, Spearman rank correlation, etc. So this measure can capture it. And it has better interpretability than those general dependence measures, which doesn't assume any relationship. So if you're interested in this, I actually gave a talk about this, I think, a conference talk, and the recording is available in our YouTube channel. So you can check that out yourself. Okay, so that's the measure. And finally, I want to say something about probably I should talk about this earlier, but since the notes somehow put it here, so I'm just going to say it. This is related to what we said, the dimension reduction. So related to dimension reduction, if you recall, for PCA, it's going to handle one matrix which we call n by p, right? Try to reduce the dimension of the columns so that hopefully we can find a new set of dimensions to encode the n data points. And related to this, we have something called canonical correlation analysis, short as CCA. And as some of you are using, I think everyone probably is using the Surat package for the single cell data. In the Surat package, it has a functionality for aligning cells of different batches. And the core of that alignment is CCA. So what CCA aims to do is to take care of two matrices, X and Y. So their rows must be matched, the same n rows. Let's say this is n by p and y is n by q. and it tries to calculate the relationship between the two matrices. Okay, how do we do that? So one thing you have already learned can handle this, the distance correlation. Distance correlation is going to compute pairwise distances of rows of X and pairwise distances of rows of Y, and then try to come up with a measure, right? But in that distance correlation, you are relying on the original P features for distance calculation and the original Q features for distance calculation. And CCA is not taking that perspective. CCA is assuming that, okay, just like PCA, you may not be really interested in the original P features and Q features, and you are okay with combining the P features into a new feature and combine the Q features into a new feature, so that you can just compute X and Y based on each new feature. That's the idea. So for the canonical correlation analysis, you are going to find the dimension reduction or linear combination of the P features here and the linear combination of the Q features here, so that you're going to maximize their correlation. Okay, so basically we need is a loading vector alpha that's p-dimensional, and another loading vector beta that's q-dimensional. So that you can see if I do x alpha, this is an n/1 vector, okay? And I do y beta, that's an n/1 vector. So I can compute the Pearson correlation between those two things. And I want to maximize it. Okay, in terms of possible alpha and beta. That's the goal of CCA. So you're going to search for a loading to combine your P dimensions and another loading to combine your Q dimensions, so that in the new dimensions of each, you're going to maximize the projected data's correlation. That's CCA. Okay, so I think I'm going to just introduce it at this very superficial level. But if you're interested, you can look into CCA. It's a very useful way for calculating correlation between two. This is still a linear correlation, linear relationship, a linear relationship between two sets of measurements, two sets of paired measurements. The rows are paired, okay? Two sets of pair measurements, but each measurement is multidimensional, and you don't really care about the original dimensions. You are okay with combining the original dimensions. So these are the scenarios where CCA will be useful. Okay, so everything we have talked so far are involving just two variables, right? Two random variables. The last part I want to say today is my colleague's work at UCLA, which is not so well known in the bioinformatics community nowadays, I would say, but to me, it's a very interesting thing. And I think I taught it every year in my class. So this is called liquid association. So now let's move on to talk about three variables. I would call this, so CCA, I would call it number five, and I'll call this number 6. For three variables, we're going to talk about this liquid association. I think this is by my colleague, Professor Carlo, who is very senior in my department, and this is his 2002 PNAS paper. So I guess one reason he named his measure liquid association is because it's short as LA. So which is is echoing the location we're at. And so what's the motivation of that? This was actually developed in the era of microarrays. So at that time, we can already measure thousands of gene expressions simultaneously. That's a really big breakthrough in both biology and statistical method development. So I think Dr. Lee observed something which is very similar to my motivation of the general R square. That is, he observed that if you have two genes, let's say gene 1 and gene 2, you look at their expression, and you find that, okay, gene 1 and gene 2 seem to be highly correlated in some samples, or positive correlated in some samples, but negative correlated in some samples. In some other samples, he observed that they do not seem to be correlated. So it's in the sense that he actually observed this pattern, and he found that this pattern can actually be explained by a third gene. So let's say that I will put those as dots, okay, to make clearer. I put crosses here. And I have some other dots here. So let's say that this negative correlation corresponds to gene 3 being lowly expressed, and the crosses corresponds to gene 3 being highly expressed, and like the dots in the middle corresponds to gene 3 being medianly expressed. So in this case, it seems that if we only look at gene 1 and gene 2, the association is not very strong. But if we incorporate another gene 3, as a conditional factor, then we can have very good interpretation. That's the motivation of his liquid association. So he wants to develop something to reflect the change. So this is to measure how the correlation of two variables x and y changes with the third variable x and y changes with z. That's the question he's going to ask. It's not just about the correlation alone, but the correlation is dynamic. It changes with the third variable z. Okay, so that's the formulation. And how did he achieve it? So of course, he wants to make the thing simple for him, right? So he doesn't want to make it too complicated. So that's why what we do is to just assume that we have three variables. Okay, this is the setting or setup. We assume that we have three scalar value variables, x, y, z, random variables, all scalar valued. And we assume that they all have mean 0. And they all have variance 1. Okay, that's the setting. We are making it really simple for us. Okay, and now let's think of the correlation of x and y given z. Oh, I should say, I forgot to say, this is my mistake. Correlation of how the correlation x, y given z, conditional on z changes with z. Yeah, this is the correct. So now let's denote this correlation of x and y given z. So we are on the population level still. We denote this as gz. It's a function of z. The function is about the thing that's in the condition. Okay, and then how do we measure the change? What's the reasonable way of defining the measurement of a change? Everyone learns calculus should have an idea. In calculus, what measures the change?
Derivative?
Exactly, yeah, the derivative. So here he really wants to measure the change related to z, right? So gz is the change. But we know z itself is the random variable, right? So it makes sense to define the liquid association. So he defines the liquid association, LA, and liquid means it's changing, of x and y given z as the expectation of this change. Expectation of g prime z, and z is the random variable in the expectation. So you see that g prime or g already taken care of x and y. It's about the correlation. So x and y are gone, and we're left with z. Now, given g prime z as the change, we take expectation. So z is gone, and then we get a quantity that's no longer random. Okay, that's the formulation. And what's really smart here is that there is something called Stein's lemma. So Charles Stein is a statistician who passed away maybe not too long ago, probably 3 or 4 years ago. And he has made a lot of fundamental contributions to mathematical statistics. He used to be a professor at Stanford. And I think in his whole career, he wrote very few papers, like 15 papers or something people said, but they are all phenomenal. So each paper has a very important impact in the field. So one of his contributions, called Stein's lemma, is a very cute mathematical result. What it says is that if Z follows standard normal distribution, then for any function G that's differentiable, its expectation of G prime Z is equal to the expectation of Z times GZ. Okay, everyone can show this yourself. Just use the integration, okay, writing down the definition of expectation as the integration of this times the density, standard normal density, and try integration by parts. Then you can see this left-hand side will be equal to the right-hand side. So this result, although it seems to be just a mathematical cute result, right? But my colleague, Dr. Lee, actually borrowed it here and make this computation of LA super easy. The reason is because given that if we assume, like based on my argument, okay, so if you have X, not just this, what I say is not only enough. So if you believe that, okay, this correlation of X and Y given Z, this conditional correlation can be expressed just as this. If we believe this can be written as X, Y given Z. So what I mean is that to achieve this, we need to have the conditional mean of X and Y and the condition equal to 0 and the conditional variance of X and Y equal to 1. Then this would hold just by the same argument I gave you in the beginning for that alternating condition expectation. So whenever this happens, then you see something magical happens. So then this expectation of ZGZ is what? This is our GZ, okay? It's just expectation of Z times conditioning expectation of X and Y given Z. Okay, and then you see for this conditional expectation, Z is a constant. I can move it inside, then I have 2 layers of expectation. By the Taylor rule, this is just expectation of X times Y times Z. So that's why the computation becomes super easy. That is, we just need to transform our data to satisfy everything we need, okay? For our data, we need to transform gene 3's measurements as standard normal distributed. That's what we need to apply Stein's lemma. And also, we need to actually satisfy this, the condition needed for this. That is conditioning on Z. We need to make X with conditional mean 0, conditional variance 1, and so is Y. So with those, then finally, we can just do the sample level. So after data transformation, let's say the transform data as triplets xi, yi, zi, okay? And for these data points, I go from 1 to n. That's our data. After data transformation, then we would compute our LA of x, y given z on our data. So I put a hat here, would just be equal to 1 over n summation to just the average of xi, yi, zi. So a very simple formula. And then how do we do the transformation? Okay, that's the key. So how to get us with a set of n numbers, how can we make them normally distributed? Or how can we make them follow the standard normal distribution? That's a technique we actually have used in quantile normalization. Recall what we did in quantile normalization is that we keep the rank, but we alter the values, right? The values are taken to be a common set of ranked values from the smallest to the largest, and they are averaged from all my previous batches. Then I replace every batch's actual values by the quantile, by the corresponding quantiles in that standard one distribution. Well, speaking of that, actually, I got a question from our YouTube video, a student's comment. I think that maybe not in our class, but someone outside of our class. And the question is, does quantile normalization reduce the rank of the matrix, of the data matrix? I think it's a very interesting question. So actually, after a very short thought about this, I think my short answer is that if your data has two columns that are purely monotone with each other, that is, if you look at two columns, so whenever this entry is high, the other entry is high, if they are monotone, which means their Spearman rank correlation is 1, then yes, you will have that issue. Because after normalization, quantile normalization, these two columns will become identical. So you will have that rank issue. But that's usually unlikely to happen for biological data. If you plot two columns, you're unlikely to see a perfect monotone relationship. So that's why I wouldn't worry about that too much. But whenever that actually happens, you may want to consider adding some small amount of white noise to your matrix to avoid that rank degeneracy. Okay, so that's the quantile normalization, just for your information. Coming back to here, so let's say that the question is given, say Z1 to Zn, how to transform them to be following standard normal. Okay, this is a technique that's quite useful in bioinformatics research. If you want to make your data satisfy a distributional assumption your method requires, then data transformation can be used. So what we want to keep is the rank for sure. The minimum should stay as the minimum, the maximum should stay as the maximum, right? So what we essentially want to do is that if our data's density, say Z, used to be like this, okay? And what I want is that after the transformation, let me call it Z star, we'll have a density standard normal. So that's what we want to achieve. And we want to do monotone transformation. So the first idea is that we will we'll record the ranks of our data. Okay, so rank. So let's say we get the ranks. So the smallest will be ranked as 1, the largest will be ranked as n. We record those as R1 to Rm. That's the first step. And second, we are going to change the ranks to percentages or left tail probabilities between 0 and 1. Okay, so what do we do? The most reasonable way is to divide each rank by n. So then the minimum will become 1 over n, the largest will become n over m. But n over n is problematic since it corresponds to a 100 percentile. And in that case, if you want to find its corresponding quantile, 100%, if you want to find the corresponding 100 percentile, for a standard normal, 0, 1, it will be positive infinity, right? You are not finding the value for that. So therefore, what we can do is that we can convert them to R1 divided by n plus 1 to Rn divided by n plus 1. So then you know the minimum. This will imply that the minimum is 1 over n plus 1, and the maximum will be n over n plus 1. So you are going to have those. And then finally, you are going to replace those by the corresponding quantile values in the standard normal distribution. So you are going to use the CDF inverse of R1 over n plus 1 to the CDF inverse of Rn over n plus 1. Okay, and this will be your new Z1 star to your new Zn star. And this set of new values will look like to be from a normal distribution, standard normal distribution. So essentially, the transformation means we keep the rank, keep the relative proportion, or I would say the empirical CDF. So that means, okay, this is the smallest, it's still the smallest, this is the largest, still the largest. For every data point, its relative rank stays, but what you change is their corresponding values, not the original value you observe, but the value that it should be from a normal distribution. So that's how we do the transformation. So I would encourage every one of you to try this yourself. So just as a recap for those of you who are not so familiar with the CDF inverse, what it actually means is that, okay, so if we have P, probability P here, then the corresponding value here is just the CDF inverse of P. That's it. The graphical illustration of what it means. So you're going to get the actual value from the normal distribution based on the left tail probabilities. So I would like to encourage you to just try this out in R. In R, you can easily get a quantiles just by the Q norm function. In the Q norm function, you input the probability, say R1 over n plus 1, you are going to get a quantile out. So just try what's R norm 0. Or R norm 0 will give you negative infinity. R norm 0.5 will give you 0. Yeah, so just like that. So you should just try to confirm this based on your understanding and see if your understanding is correct. Okay, so that's it. So I think it's a very quick overview of the associations. Yeah, actually, I spent less time on this than in my previous years. I think the reason is that we spent more time to cover some other materials we didn't do in previous years, like in the beginning we spent more time to talk about like the statistic basics. So for the remaining lectures, we have 2 lectures to go, and then we will have your final presentation on Thursday of week 10. For the remaining 2 lectures, I still plan to talk about the sampling methods, the Monte Carlo methods, and the NCMC. So these 2 methods, very different from what we have said so far. They are not statistical models. They are not about a probabilistic model of data, but they are using probability to help us draw but they are methods for us to draw samples from a probability distribution. So that's why they are called sampling method. And probably I can just say a little about the intuition or the motivation. Why do we want to do that? It's used, sampling methods, Monte Carlo methods is used when you cannot easily do mathematical integration of a complex function. So when integration becomes very complicated, so that will give you some hurdle in the calculation of expectation, because expectation is naturally an integration. If the density is too complicated, and that could happen in Bayesian statistics, where we will work with the posterior, and the posterior could be a very complicated form. So in that case, how would you do the integration? Not easy. So what you do is that you just treat the posterior as a probability density. If you can draw observations from that density, that can be considered as your sample. Then based on the sample, you can compute an average. That's an easy computation. And you hope that sample average is a good approximation to the expectation. So as you are doing the sampling yourself, so you initiate the sampling, you can control the sample size. You can draw a large enough sample from the density, the posterior you specify. Then you can just have a very good approximation accuracy for the expectation you need. So that's the whole story why we want to do sampling and why we want to be able to draw samples efficiently from a complicated distribution. In some cases, like in Bayesian statistics, we don't even know the normalization constant of the posterior. That means that even though we know the posterior is proportional to something, but without that normalization constant, the posterior is not yet a valid probability density, which means it doesn't integrate to 1. So in that case, integration is not possible. But you can still draw, you still want to be able to draw a sample from that unnormalized density in some way. So that's why MCMC was proposed. So just in short, don't confuse MCMC with hidden Markov models you learn from some other classes, even though they both rely on Markov chain, but they are different. Hidden Markov model is about a probability model, which you assume that the data is generated from. So it's a model. While MCMC is a sampling technique for you to draw samples from a complex density. Okay, so we will start our discussion on that new topic starting from our next Tuesday. And that's all for today. And so please start early on your project, and I really look forward to your presentation in week 10.